Hello and welcome to this pre-recorded lectures about electric motors. My name is Per Marklund and I will try to guide you through electric motors from a mechanical engineering point of view. We will not dig deep into how they work, but we will look into torque characteristics and the basics, how they function. And we will try to discuss how these different types of motors can be used in different applications and pros and cons with different systems. So we will discuss a lot of things like DC, AC, asynchronous, synchronous motors, brushless, induction motors, etc. So if we then look at the electric motor and the basic principle of how it works, we have always some kind of coils, which you normally call windings when you talk about electric motors, and this generates magnetic fields. In some motors you combine these windings with permanent magnets as well, but that's not always the case. We will discuss the components of the motor by looking at this figure, which is a normal brushed DC motor with permanent magnets. The motor has a stationary part, which is called the stator, and that basically consists of two permanent magnets. It has a rotating part connected to the output shaft, which is called the rotor. And when then the magnetic field of the rotor and the stator are different, the magnetic forces will try to turn the rotor, as you can see here, this blue and red arrow. And if the magnetic field in either stator or rotor is controlled so that there will be always some force acting on the rotor, it will continue to rotate, and then we have a motor. And how this magnetic field is controlled is basically the main difference between different types of motors that we will discuss in this lecture. So we know that we change the magnetic field to make the rotor rotate, but how do we do that? Well, here are a number of different motor types that are used in machines all around the world. We have the DC motors, and DC is, as you know, direct current, like if you power it from a battery, for instance. And there you have the brushed motor, or you have the brushless motor. The interesting thing is that the brushless motor is actually not a DC motor. In reality, it is an AC motor that is controlled with a type of frequency drive directly from normally the battery or the direct current source. But we will come into that. If you look at AC motors, alternating current, there are many different kinds. First, we have the synchronous motors, where the RPM is proportional to the frequency, meaning that, for instance, if the motor has 1000 RPM, if you power it with 50 Hz, it will have 2000 RPM if you power it with 100 Hz. So it follows in sync, and that's why it's called synchronous motor. And that could be, for instance, a permanent magnet motor, or a synchronous reluctance motor, or a combination between these two. IPM syn RM, internal permanent magnet synchronous reluctance motor, tricky word. And they can also be asynchronous, which is normally what we call an induction motor. But if we go back to the DC motor and start to look at that first. Here we have a DC motor with brushes. A brushed motor has brushes made from graphite, which distribute the electric current to the rotor, activates different electric windings, and makes the rotor rotate. In this case, the stator also has windings. You can see field windings, but the field windings could also have been replaced with permanent magnets. So, as you can see in this brushed motor example, we don't have any permanent magnets. But in other brushed DC motors, we could have permanent magnets on the stator. This example is a starter motor to an internal combustion engine. Here we can see another type of brushed motor, this one with permanent magnets on the stator. This is a simple motor type, mass produced, very cheap, often used, for instance, in automotive industry, like in subsystems, like when you open and shut the windows on the car, for instance. And why do you use that? Yeah, as I said, it's cheap. That's of course one reason why you want to use it. But also, if you look at the torque characteristics here we have normalized the torque curve. So TQS is the maximum torque, and omega 0 is the rotational speed at zero load. So when omega divided by omega 0 is 1, you have the maximum speed, and when TQ divided by TQS is 1, you have the maximum achievable torque. What's interesting here is you can see that the torque is the maximum torque when the rotational speed is 0, when it's stationary. So we have a really high starting torque, which is of course good in such application when, like I told you about in the automotive industry, when the windows are going up and down, because normally you need some torque to get them moving from the beginning. If you look at the power output, obviously the power output is 0 when the rotation speed is 0, because the power output is torque divided by rotational speed. This means that the maximum torque is at 0.5, 50% of the maximum rotational speed. However, this is the power output. The power input to the motor could be something else. So we could have a quite high power input to the motor at 0 rotational speed. This means that the brushes and windings may be destroyed by low rotational speed and bad cooling, even if the power output is 0. Another type of DC motor is the brushed motor serial magnetized. And this is interesting because, as an example, I show a corded drill which you power from a socket in the wall, 230 volt AC. And I talk about this as a DC motor. And I will come to why. In a serial magnetized motor, field and rotor windings are connected in series. You don't have any permanent magnets in this type of motor. But since you have a brush that is sort of changing the field, it's always the opposite in the rotor and the stator, so it doesn't matter actually if you have AC or DC. So sometimes you call this for a universal electric motor. It works with both AC and DC without any fancy control system. So the build-up of this DC motor is normal DC motor, but it could also work with AC, and often it is actually used as an AC motor. Therefore, it also have the same characteristics as the permanent magnet DC brushed motor, meaning that you have a high torque at low speed, which is of course very good to have in such an application like the corded drill. It has a predetermined rotational direction, which can be shifted by shifting the field or rotor windings, the direction of the current in those. There also exists parallel magnetized instead of serial magnetized motors, but they have similar features, so we don't have to talk about them separately. If you then go into brushless motors, I said in the beginning that the DC brushless motor isn't actually a DC motor. Actually, it is a magnetized synchronous motor with permanent magnets. So it is an AC motor, and therefore you need a special regulator or speed controller to work. So that speed controller, like this radio control electric speed controller, it takes a DC from the battery and makes it into a controlled AC suitable for this motor. Normally they have 3 connection cords, meaning that it's a 3-phase motor. It has a high efficiency, much higher than the brushed motors, around 90 and even more, and the brushed motor only have around 70. It's because of the need for this control system, it is actually quite expensive in comparison to the brushed DC motor. But you also get you get the higher efficiency and also the good controllability of this instead. So you pay for the higher performance, you can say. If we then move into AC motors, and first we talk about synchronous motors. As I said, synchronous motor means that the rotation speed is synchronous with the frequency. If you double the frequency, you double the RPM of the motor. Synchronous AC motors of different kinds. Yeah, there exist different types of synchronous AC motors. First we have the permanent magnet motor, which gives a high starting torque, but also poor efficiency at really high RPM due to back EMF issues. Back EMF is some magnetic counterforces that will sort of counteract the motion of the rotor when you have high RPMs. This is also the same as you experience in a brush DC motor with permanent magnets, and the reason why you have a specific top speed of such a motor. In the middle we have the synchronous reluctance motor. Here we don't have any windings or any permanent magnets in the rotor. We have a ferromagnetic rotor where non-permanent magnetic poles are induced by the stator windings. This generates torque through magnetic reluctance. But due to how this works with the magnetic reluctance, it actually performs much better with higher speed, and it doesn't perform very good at low speeds. So then we have one motor that performs good at low speeds, the permanent magnet motor, and one that performs good at higher speeds, the synchronous reluctance motors. And what we can do is to put these two together and get an internal permanent magnet synchronous reluctance motor, or IPM Syn RM. Difficult word. This combines then the benefits of a permanent magnet motor and a synchronous reluctance motor. can combine the higher and smoother starting torque from a permanent magnet motor and better efficiency and higher RPM from a synchronous reluctance motor. And basically what you do is that when you make an internal permanent magnet synchronous reluctance motor, is that you take the rotor from a synchronous reluctance motor and you mount permanent magnets in the slots in the rotor, like we can see on this figure. By controlling the angular offset of the magnetic field from the stator by the frequency drive, it is possible to choose if the motor is operated as a synchronous reluctance motor or a permanent magnet motor. So we can sort of switch mode with a good control system. So you have one motor when it's low RPM, and you have another motor characteristics at higher RPM. This is used in some electric car manufacturers. And then we have the asynchronous motors, which are often called induction motors. And this is the most common motors in various machines and equipment that are powered from the three-phase in the power grid. An asynchronous motor is a motor with a cage rotor that is short-circuited, where you induce some current by the stator windings. And that's the most common type of three-phase or also two-phase motor for machines without variable motor speeds. You can also have a frequency drive to change, because if you double the frequency, you also double the RPM of an asynchronous motor. However, it's not forced to go in exactly that RPM. You can lose several hundred RPM and it still operates, which is not possible with a synchronous motor. If you lose several hundred RPMs on a synchronous motor, it will just stop work because it can't power itself with such a difference between the synchronous speed and the real speed. The benefit with this asynchronous motor, called induction motor, is that it can start directly from the grid with a simple switch. Since you have always 50 Hz in the power grid, if you then start it, of course, from start the rotation speed is 0, so it's very far away from the speed it's supposed to rotate in. But it can start from that speed as well, and then reach the set speed for the motor. What's good to know with these type of induction motors is that you can choose normally what kind of operation voltage you want to operate it with. Often a three-phase induction motor can be set for operation at different voltage. For instance, 230 volt, which is our normal voltage for one-phase system, or 400 volt through so-called delta Y connectors within the connection box on the motor, as you can see on this figure. By moving some connectors, these yellow ones on the figure, you then change if it will work as a delta or a Y connected induction motor, which also means that you will change the suitable voltage that it's operating with. Here is one example on the mark plate where you can see delta Y, where delta then is 230 volt and Y is 400 volt. And you can also operate one of these three-phase motors if you only have a one-phase cable available. Then you set the three-phase induction motor in delta mode, meaning that it wants to operate at 230 volt. And you connect, for instance, phase 1, input phase 1 L, which is shown as L1 in the figure, to the phase, L2 to the neutral, and then you take a capacitor of suitable size, and there are tools how you calculate this size depending on the motor size and the RPM, etc. So you take this capacitor and put it between the remaining cable, L3, and either L1 or L2. And then it will work also with one phase. And this is something that is very often used in different machines around us. The characteristics of the asynchronous motor is that if we have the speed as in the maximum speed, then we have no torque. But when it starts to, as we say, it starts to slip, when the rotation speed is less than the maximum speed, you will get higher and higher torque until you reach the maximum, which is normally around 80% of the maximum speed. So if the maximum speed of the motor is 1000 RPM, you will have the maximum torque at 800 RPM. And then if it's getting lower and lower from that, you also lose some torque, but you see that it will never go below around 60% of the maximum torque. And this is why you can actually start one of these asynchronous motor directly from the power grid with the on-off switch. The power output will look like you see here to the right, where the maximum power is also slightly above 80% of the maximum rotational speed. If you want to do simulations of electric motors, there are two fundamentally different types of simulation that you can do. When you want to use them in a simulation model to describe an electromechanical system. I call them 1 and 2 in this case. The simulation type 1 is if you are really interested in the dynamics of this motor. For instance, a startup sequence. You want to see how many seconds it takes to start to rotate. Where you have a large variation in RPM and high acceleration, like if you want to simulate an acceleration phase in a car or something. And here you have some important parameters. You have the resistance, you have the inductance, and you also have this electromotive force, which is called then the back EMF that we talked about previously. Often these models, they become very, very complicated. However, if you only have a simple DC brush motor with permanent magnets, it's quite simple to model, and you have this link here that you can use to make a simple simulation model of the dynamic behavior of a brushed DC motor. But often we don't really care that much about the dynamics. We have some type of quasi-static approach, and that's sufficient. If you are interested in exactly how it works with the fast acceleration and so on, we want to monitor energy consumption over a longer time or something like that, then we can instead use data sheets, power or torque curves, or lookup tables as input to the simulation model of your mechanical system. And in this course you will try both of these different types, the dynamic one or the one where we are simulating longer sequences and the dynamic behavior isn't really important. This is then the simulation of the dynamic behavior of a DC motor. And you can follow this link and build up this Simulink model yourself. But what we have here is a simplified model of the DC motor. We have a resistance that reduces the current. We have an inductance, which is sort of a resistance towards changing current due to the coils inside the motor. And we have the electromotive force, back EMF, that is counteracting voltage due to changing magnetic fields. And the system you simulate looks like this. You have a flywheel on a brushed DC motor, and you have a battery that powers it. And this example actually is a good example that shows how back EMF limits the maximum rotational speed of the brushed DC motor. And as we discussed, similar limitations can be found on permanent magnet synchronous AC motors, which, for instance, may limit the top speed of an electric car with such a motor. And as you can see, this is how the Simulink model will look like. It is fairly simple, even if you're simulating something that abstract as an electric motor. But follow the instructions in the links and you will understand much more about how this engine is built out and how it behaves during a startup sequence. So, we have been discussing a lot about the control system and how we control the AC motor with frequency. And to do that we use frequency drives, or sometimes we call it variable frequency drives, VFD. So the frequency drives, they are used to control RPM for AC motors, and they convert 50 Hz from the grid to the chosen frequency to then control the speed of the motor. It can convert one phase to three phase, and this also eliminates the need for mechanical RPM control. Maybe you don't need a gearbox or a transmission where you can change gears and change the output RPM. It enables soft start of the motor, and by this you can also save a lot of energy. So you feed it with 50 Hz, and then depending on what you want to do with the motor, you get an output frequency that is controlled by the frequency drive. Also, if you have an electric vehicle or something that is controlled by a battery, it's basically the same, but instead of feeding it with one phase or three phase, you feed it with a DC current. So the principle is the same, but you don't need the first part of the frequency drive. And next slide will show how the frequency drive is built up. You have first a rectifier that converts AC to DC, and if you start with the battery, meaning DC, you don't need this part. And then you have the mid part that adjusts the current, and then you have the frequency controller at the end that converts DC to AC again with a variable frequency. You have first a rectifier that converts AC to DC, and if you start with the battery, meaning DC, you don't need this part. And then you have the mid part that adjusts the current, and then you have the frequency controller at the end that converts DC to AC again with a variable frequency. But there are also some disadvantages with frequency drives. One is that the output voltage might be noisy. This could interfere with other systems, like if you have sensitive sensor systems, etc. in your machine. And you also can get a higher risk of overloading and overheating, because normally the cooling fan of a motor is mounted on the shaft, which means that if you control it with the frequency drive, so you have a low rotational speed, you also have a low fan speed and a less cooling effect, and still you can have a high power in the motor. So that could lead to a risk of overheating. If you look at the efficiency of electric motors, as we have been discussing on previous slides, we know that it is in general quite high. For some motors, especially the brushless types, we can have efficiency on 90 and even more percent. However, just as for the internal combustion engine, where we have looked at the brake-specific fuel consumption plot, the BSFC, the efficiency of the electric motor also varies depending on how it is used. Therefore, it's important to use the electric motor with the best possible gear ratio to have an efficient operation as possible. Here we can see one example of electric motor made for the vehicle industry. And actually, if we look here to the right, it looks fairly similar to the BSFC of an internal combustion engine. This is made for heavy duty traffic, so we have very high torques in this case. You can see they go up to 2000 Newton meters. But what's interesting is that we have also here a sweet spot where we actually would like to be. In this case, it's around 1000 RPM and between 300 to 900 Newton meters. In that area, you have an efficiency of almost 94%. But if you have really high RPM, like over 4000, you see that the efficiency goes down to around 70%. And also, where you have really low speed, you also have a low efficiency. So that's why we need to choose a gear ratio that makes us use the motor in the correct area in this plot, so we can have a high efficiency and we have enough torque and correct RPM for the application. We also see that if you look at the torque curves to the left, we see that the torque can normally be quite a lot higher if only for a short duration of time. The continuous torque is always much lower because of the cooling reasons. If you continuously have a high torque, meaning a high power, you need to cool away a lot of energy. But for an electric motor, normally it is not an issue to have a torque peak for a few seconds. So you can have a smaller engine that you overload in a short duration of time without getting into problems. Another special type of electric motor that I will only mention is the linear motor. Basically, it's the same principle as a normal motor we have been discussed previously, but instead of having rotational motion, you have a linear motion as shown below. What you do is that you convert electric current directly to a linear motion instead of having to use an electric motor with a rotating shaft and some transmissions to get this linear motion. This is used in linear actuators, but also in other applications like maglev trains, etc. Step motors are also a special type of electric motors. Normally, when we talk about electric motors, they are rotating with a certain RPM. But a step motor, you can instead make rotating 60 degrees and stop there. For instance, if you have a 3D printer, you have seen all the step motors that are used for controlling all the different motions in X, Y, and Z, and also the extruder of the filament. These are very good if you want to have slow rotational speeds with a super high precision. However, there is no feedback in a step motor, and you can lose its position if overloaded. So you can think of it like the motor don't know where it is, but it only knows the number of steps it took to go there. So if you tell it to move 10 steps counterclockwise, and then it's overloaded, so it only takes 8 steps, you will have a smaller angle, obviously. But you don't have any feedback that tell you that you actually don't have the angle that you want it to have. And this is why you normally calibrate these over startup. For instance, if you have a car with electric gauges, you sometimes can see that when you start up the car, it goes from 0 to maximum to 0, which is normally a calibration sequence for the step motor in the, for instance, RPM gauge. This also looks cool maybe for the user, but the main reason why they do it is to calibrate the step motor.